Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we will be exploring HVAC thumb rules with examples. This is a fundamental topic that can really help in designing and maintaining efficient heating, ventilation, and air conditioning systems. We'll go over some key rules and see practical examples to better understand how they work in real-world scenarios. So, without further ado, let's dive into our first slide. Welcome to Process Piping Hub. Today, we're diving into HVAC design thumb rules. These are simple, practical formulas that every engineer should have in their toolkit. We'll cover everything from estimating cooling loads to sizing ducts and understanding airflow basics. These quick rules are designed to save you time and make your design process much smoother. Be sure to stay with me until the end, because I'll be sharing some real-world examples and professional tips that can really make a difference in your work. So, let's get started and make HVAC design easier and more efficient. Let's take a closer look at the cooling tower and ventilation systems. These are essential components in maintaining optimal temperature and air quality within the facility. Cooling towers help remove heat from the process or HVAC systems, ensuring everything runs efficiently. Ventilation, on the other hand, is about controlling airflow and ensuring fresh air circulation, which directly impacts indoor air quality and comfort. Both systems work together to create a safe and efficient environment. As we progress through this presentation, you'll see how these elements connect with other parts of the system, like air distribution, system parameters, and water management. Understanding these fundamentals is key to designing and operating effective cooling and ventilation solutions. Welcome to Cooling Basics. Today, I want to walk you through some fundamental concepts about cooling systems. First, cooling is all about removing heat to maintain a comfortable or safe environment, whether in a building, a machine, or even electronic devices. It's essential because excess heat can cause equipment failure or discomfort. When we talk about cooling, we often focus on key components like heat exchangers, fans, and refrigeration cycles. These work together to transfer heat from the object or space that needs cooling to the outside environment. It's also important to understand the difference between sensible cooling, which reduces temperature, and latent cooling, which removes moisture from the air. Both are crucial depending on the application. Connecting this to our overall theme, effective cooling not only ensures comfort, but also enhances the efficiency and longevity of equipment and systems. So, grasping these basic principles sets the foundation for understanding more advanced cooling technologies and their applications. In this slide, we're looking at a practical way to estimate the cooling power demand for HVAC systems, especially during the initial design phase. This method is very useful for getting a quick estimate before diving into detailed load calculations. The key here is the concept of tons of refrigeration, or TR, which is a common unit used in the industry. 1 TR equals 3.517 kilowatts. To put that into perspective, if you have a 10 TR cooling system, it would provide approximately 35.17 kilowatts of cooling capacity. This conversion makes it easier to relate the refrigeration capacity to electrical power, which is often what we're working with in system design. Now, let's talk about what exactly a TR is. A ton of refrigeration is defined as 12,000 BTU per hour. It represents the cooling capacity needed to freeze 1 ton of water at 32 degrees Fahrenheit within 24 hours. This standard gives us a practical understanding of how much cooling power is involved. Understanding these conversions and definitions helps us apply this knowledge effectively in designing HVAC systems. It allows us to quickly estimate the cooling load and select appropriate equipment, ensuring efficiency and proper sizing from the start. Let's talk about the standards for sizing cooling systems based on space. For small residential systems, we typically use a rule of thumb, 1 ton of cooling capacity per 500 square feet. For example, if you have a 2,000 square foot home, you divide 2,000 by 500, which gives you 4 tons. This approach is suitable for smaller residential spaces where the load is relatively straightforward. Now, shifting to commercial spaces like offices, the standard changes a bit. Here, we usually consider 1 ton of cooling per 300 square feet. So, for a 3,000 square foot office, we divide 3,000 by 300, resulting in about 10 tons of cooling needed. This helps us get a good initial estimate for system sizing. The key takeaway is that these standards serve as a starting point for determining the cooling load. They're useful for initial planning, but always remember that actual loads can vary based on specific space characteristics. Understanding these basics helps ensure we select the right system size, maintaining efficiency and comfort across different types of spaces. Let's talk about the standard cooling loads for different types of spaces. For spaces like offices or conference rooms, the general guideline is about 1 TR for every 100 to 150 square feet. This higher sensible load is mainly due to dense occupancy, meaning more people generate more heat, and the space itself. For example, if you have a 1,000 square foot auditorium, you would typically need around 7 to 10 TR to keep it comfortable. Moving on to auditoriums or theaters, the standard is slightly different, about 1 TR per 150 to 200 square feet. The reason for this higher ratio is because these spaces often include cooking or heating equipment, and they tend to have even denser occupancy at times, which adds to the cooling load. Take a 1,200 square foot kitchen, for instance. It would require roughly 6 to 8 TR to ensure proper cooling. The key point here is that each space has its own specific cooling load needs, which depend on occupancy, equipment, and usage. Understanding these standards helps us size our cooling systems accurately and efficiently, ensuring comfort while avoiding over- or undersizing. This is all part of designing effective space-specific cooling solutions that match the unique demands of each environment. Now, let's dive into airflow and load calculations. These are crucial steps in ensuring our system is both efficient and effective. When we talk about airflow, we're really focused on making sure the right amount of air moves through the space, enough to maintain good air quality without wasting energy. Load calculations, on the other hand, help us determine how much heating or cooling is needed to keep the environment comfortable. By accurately calculating airflow and loads, we can properly size our equipment, which saves us money and improves overall performance. It's all about balancing the system to meet the specific demands of the space while staying energy efficient. This part of the process ties directly into the overall theme of designing sustainable and reliable HVAC systems. When done correctly, it ensures comfort, safety, and efficiency in the long run. Let's take a look at how airflow, measured in cubic feet per minute, or CFM, is calculated. The basic formula is the room volume multiplied by the air changes per hour, or ACH, divided by 60. For example, if you have a 5,000 cubic foot room and you want 10 ACH, you would calculate 5,000 times 10, divided by 60, which gives you 833 CFM. This is a key calculation used in ventilation design to ensure proper air exchange. Now, moving on to how HVAC systems are sized, particularly in terms of airflow. Typically, for proper heat transfer, HVAC systems require about 400 CFM per ton of cooling, or TR. So, if you have a 10 TR cooling system, it needs approximately 4,000 CFM of airflow. This is essential when sizing air handling units, like AHUs and FCUs, to make sure they perform efficiently and meet the cooling load. To summarize, understanding both the airflow calculations based on room size and ACH, as well as the standard airflow per ton, helps us design effective ventilation and cooling systems. These principles are fundamental to ensuring comfort, efficiency, and proper system operation in any building. Let's take a look at typical ACH values for different space types. For office spaces, the recommended range is usually around 6 to 10 ACH, which helps maintain good indoor air quality and comfort for occupants. Residences, on the other hand, typically require lower airflow, around 4 to 6 ACH, because the indoor environment needs to be comfortable but not overly ventilated. For example, imagine we have a 5,000 cubic foot office with an OC of 8. To meet this standard, it would need approximately 667 cubic feet per minute, or CFM, of fresh air. This ensures that the indoor air quality is maintained at a healthy level, preventing issues like stale air or buildup of indoor pollutants. Understanding these ACH standards is key to designing effective ventilation systems. It helps us balance energy efficiency with occupant comfort and health. When we specify ventilation rates based on space type, we're making sure the indoor environment remains safe, comfortable, and compliant with standards. Now, let's take a look at how lighting impacts the cooling load. Typically, lighting adds about 1.5 watts per square foot to the cooling demand. For example, in a 1,000 square foot office with standard lighting, this means about 1.5 kilowatts of heat generated just from the lights alone. This directly increases the cooling requirement, so lighting design is an important factor to consider. Next, let's consider the heat contributed by the occupants. Each person sitting in a space contributes roughly 500 BTUs per hour. So, if you have 20 people in the room, that adds up to about 10,000 BTUs per hour, or approximately 0.83 tons of refrigeration. This is a significant sensible load in occupied spaces because people are constant sources of heat. Understanding these components, lighting and occupant heat, is crucial because they form the core parts of the overall cooling load. When designing or analyzing a cooling system, accounting for these sensible loads helps ensure we size the system correctly and maintain comfort efficiently. Let's talk about infiltration first. It accounts for about 10 to 15% of the total sensible load in a building. For example, if you have a system with a total load of 50,000 BTU per hour, roughly 5,000 BTU per hour could come from air leaks around doors and windows. This infiltration heat gain is important because it adds to the cooling load, and understanding it helps us design more efficient systems. Now, moving on to equipment heat contribution. Equipment can add roughly 2 to 4 watts per square foot. To put that into perspective, imagine an office space of 500 square feet. If the equipment load is about 3 watts per square foot, we're looking at an additional 1.5 kilowatts of heat. This is especially critical in spaces like IT rooms or commercial areas where equipment usage is high, because it significantly impacts the cooling requirements. So, in summary, infiltration and equipment are key components of the cooling load. They might seem small at first glance, but they can add up and make a big difference in how we approach system sizing and efficiency. Recognizing these factors is essential for designing effective and energy-efficient cooling solutions. Let's take a closer look at Slide 13, which focuses on system parameters and air handling. When we talk about system parameters, we're really referring to the key settings and specifications that define how our system operates. These include factors like airflow rates, temperature controls, and humidity levels, all of which are crucial for ensuring optimal performance. Air handling, on the other hand, involves the processes and equipment responsible for moving, filtering, and conditioning the air within the system. Proper air handling is essential for maintaining air quality, energy efficiency, and comfort. Connecting these points to our overall theme, understanding and optimizing system parameters and air handling is fundamental for achieving a balanced and efficient environment. It's about making sure our system performs reliably while also being energy conscious. In essence, paying attention to these details helps us deliver better indoor air quality and system longevity, which are key goals in our project. Let's talk about relative humidity, or RH, which should ideally be controlled between 50 and 60%. Maintaining this range helps us achieve a good balance between comfort and system efficiency. For example, if the air temperature is 24 degrees C with about 55% RH, that creates a comfortable environment while also allowing the HVAC system to operate effectively. Moving on to optimal humidity levels, keeping the RH within this range is crucial for both comfort and performance. It's important to remember that these numbers aren't just arbitrary. They're backed by standards in HVAC design to ensure people feel comfortable and systems run smoothly. Now, regarding room temperature, the recommended standard is around 24 degrees Celsius, give or take about 1 degree, so anywhere between 23 and 25 degrees C. This range is widely accepted because it provides the best comfort for most occupants. Finally, I want to touch on room conditions and water flow standards. Ensuring proper water flow is essential for system efficiency and maintaining the right environmental conditions. When all these elements, temperature, humidity, and water flow, are properly managed, it results in optimal performance and comfort in the space. Let's talk about the standard delta for chilled water. Typically, it's around 10 degrees F, which is roughly 5 degrees C. To give you an example, the supply water might be at 44 degrees F, and it warms up to about 54 degrees F when it returns. This temperature difference is fundamental because it directly influences how we design the coils. Next, regarding the chilled water flow rate, we usually consider about 2.4 gallons per minute per ton of cooling. So, for a 10-ton system, that would mean a flow rate of 24 GPM. This is a critical factor because it impacts the sizing of both the chiller and the pumps, ensuring they operate efficiently. Finally, when we look at room conditions and water flow standards, these numbers help us set the right parameters for system performance. By understanding these key points, delta, flow rates, and room conditions, we can optimize the entire cooling system to run smoothly and effectively within the overall design parameters. Let's talk about coil airflow ranges. Typically, they fall between 350 and 450 CFM per ton. For example, a 10-ton coil usually needs around 4,000 CFM of airflow. This is a key factor in guiding our selection of air handling units and ensuring they perform efficiently. When we're designing or selecting equipment, understanding these airflow requirements helps us match the coil capacity with the proper airflow. It's all about making sure the system operates smoothly and effectively. Remember, matching airflow with coil size is crucial for optimal performance and energy efficiency. Now, let's take a closer look at the air velocities for branch and main supply ducts. For branch ducts, we aim for an operating range of about 700 to 900 feet per minute. This range helps ensure quiet air distribution, which is critical for maintaining comfort without excessive noise. For example, if we have a branch duct carrying 900 CFM, it typically needs to have a cross-sectional area of about 1 square foot to achieve that velocity comfortably. Moving on to the main supply duct, the target velocity is slightly higher, around 1,000 to 1,200 feet per minute. This is because the main duct needs to handle a larger volume of air, say 4,000 CFM, and still operate efficiently without creating too much pressure loss or noise. To achieve this, a 4 square foot duct area would be appropriate. Overall, these guidelines help us balance pressure, airflow, and noise levels, ensuring the system runs smoothly and efficiently. Remember, proper duct sizing and velocity control are key to a well-designed ventilation system that performs reliably and quietly. Let's talk about maintaining the duct aspect ratio, which should be kept at or below 4:1. Why is this important? Well, a proper aspect ratio helps minimize friction loss within the duct system. For example, if you compare a 24-inch by 6-inch duct to a 30-inch by 4-inch duct, the 24 by 6-inch duct is actually better because it offers lower airflow resistance. Keeping the aspect ratio within this limit ensures that air moves efficiently without unnecessary pressure drops, which is crucial for system performance and energy efficiency. Now, moving on to diffuser outlet velocity. This should typically be between 400 and 600 feet per minute. Why? Because this range ensures a comfortable airthrow, which is essential for occupant comfort. For instance, a diffuser that handles about 400 CFM usually has an outlet area of around 0.8 square feet. Maintaining these parameters helps us deliver proper airflow while avoiding drafts or noise. In summary, paying attention to duct aspect ratios and diffuser velocities helps us design systems that are both efficient and comfortable for users. Now, let's talk about the allowable duct pressure drop, which typically ranges from 0.08 to 0.12 inches of water gauge per 100 feet of duct. This means that for a duct run of about 200 feet, you can expect a pressure loss between 0.16 and 0.24 inches of water gauge. This is a critical factor to consider because it directly impacts how we size the fan. If the pressure drop is too high, the fan will need to work harder, which can affect efficiency and energy consumption. So, maintaining the pressure drop within these standards ensures optimal airflow and system performance. Remember, these guidelines help us design duct systems that are both effective and energy efficient, keeping the entire HVAC system running smoothly. Let's take a closer look at the fan, pump, and water systems. These components are critical to many industrial processes and building operations. Fans are essential for moving air, whether for ventilation, cooling, or process requirements. Pumps, on the other hand, are used to transfer liquids, whether it's water, chemicals, or other fluids, ensuring smooth operation of systems that depend on fluid movement. Water systems encompass everything from supply and distribution to treatment and recycling, playing a vital role in maintaining system efficiency and safety. Understanding how these elements work together helps us optimize energy use and prevent failures. As part of the overall system, they highlight the importance of proper design, maintenance, and control to keep operations running smoothly and efficiently. Let's talk about fan efficiency first. Typical fan efficiency usually falls between 70% and 85%. For example, if you have a fan with a 5 kW input power, it will deliver an output power somewhere between 3.75 and 4.25 kW. This range is really important because it directly affects how much energy your system consumes and how well it performs overall. Now, moving on to total pressure. The total pressure that a fan produces is actually the sum of static pressure and velocity pressure. To put that into perspective, if your static pressure is 2 inches of water gauge and your velocity pressure is 0.5 inches, then your total pressure is 2.5 inches of water gauge. Understanding this is critical because it helps you select the right fan curve for your system, ensuring you get the performance you need without oversizing or undersizing. In essence, both efficiency and total pressure composition are key factors in designing and operating effective fan systems, impacting both energy use and system performance. Let's talk about static pressure margin requirements. A 10% static pressure margin is generally recommended to account for installation losses. For example, if your design pressure is 2.5 inches of water gauge, you should select a fan rated for around 2.75 inches of water gauge. This extra margin helps ensure that even after installation, the system performs as intended. Moving on to fan power calculation, the key formula is fan power in kilowatts equals the airflow rate times the pressure drop, divided by 102 times the efficiency. To put that into perspective, if you have an airflow of 10,000 CFM and a pressure drop of 2 inches of water, the power required is approximately 1.9 kilowatts, assuming 75% efficiency. Understanding these concepts is crucial because they connect directly to the overall performance and efficiency of your ventilation system. Properly accounting for static pressure margins and accurately calculating fan power ensures reliable operation and helps optimize energy consumption. Let's start by breaking down the concept of pump total head. Essentially, the total head that a pump needs to overcome is the sum of 3 main components: friction losses, static head, and fitting losses. For example, if we have 20 meters of friction losses, 5 meters of static head, and 5 meters of fitting losses, then the total dynamic head the pump must handle is 30 meters. This calculation is crucial because it directly impacts the pump selection process. Choosing a pump that can handle this total head ensures reliable system operation. Moving on, understanding the total pump head components helps us grasp how different factors affect pump performance. Friction losses are caused by fluid resistance within the pipes. Static head relates to elevation differences, and fitting losses come from valves, elbows, and other fittings. All these add up to define the pump's required capacity. Now let's look at flow rates, which are equally important. For chilled water, the flow rate is typically around 2.4 gallons per minute per ton of cooling, or GPM-TR. So, for a 20-ton system, that's about 48 GPM. Similarly, for condenser water, the flow rate is roughly 3 GPM-TR. For example, a 100-ton chiller would need about 300 GPM. These flow rates are critical because they directly influence how we size both the chillers and the cooling towers to ensure efficient heat transfer. Finally, understanding these basics of chilled and condenser water flow rates helps us optimize the entire HVAC system. Proper pump sizing based on these calculations ensures energy efficiency, system reliability, and effective cooling performance. So, always keep these key points in mind when designing or evaluating these systems, because they form the foundation of effective system operation. Let's talk about the velocities for chilled water and condenser water pipes. For chilled water, a typical velocity range is between 1.5 and 2.5 meters per second. For example, if you're using a 2-inch pipe with a flow rate of 2 liters per second, that falls well within the acceptable range. Maintaining this velocity helps ensure the system runs quietly and smoothly, reducing noise and minimizing friction losses. Now, for the condenser water pipes, the recommended velocity range is slightly higher, about 2 to 3 meters per second. To illustrate, a 3-inch pipe carrying around 5 liters per second would have a velocity of roughly 2.5 meters per second, which is ideal. Keeping the flow within these ranges is crucial for low noise operation and efficient pumping. Moving on to pump efficiency, most pumps operate between about 65% and 80%. So, if you have a pump with a 5 kilowatt input power, it might deliver roughly 3.25 to 4 kilowatts of hydraulic power. This efficiency is key for designing energy-efficient systems because it ensures you're getting the most out of your pump with minimal energy waste. Understanding these basic sizing and efficiency standards is essential for creating reliable, energy-efficient chilled water systems. Proper pipe velocities and efficient pumps go hand in hand to optimize performance and longevity of the system. Let's now turn our attention to air distribution and quality. These are crucial elements in any ventilation system because they directly impact indoor comfort and health. When we talk about air distribution, we're referring to how well the air is circulated throughout a space, ensuring that every area receives the appropriate amount of fresh air. Proper distribution helps prevent hotspots or stagnant zones, which can compromise air quality. Air quality itself is about more than just oxygen levels. It involves controlling pollutants, humidity, and ensuring the air remains clean and healthy to breathe. Good air quality can reduce health issues, improve productivity, and create a more comfortable environment overall. It's important to highlight that effective air distribution is closely linked to maintaining high air quality. If the air isn't properly circulated, contaminants can accumulate in certain areas, negating the efforts to keep the environment healthy. This ties back to our overall goal in building design, to create spaces that are not only energy efficient, but also promote well-being through optimal indoor air quality. So, paying attention to these factors ensures we meet both comfort and health standards. Let's talk about office environments and how we ensure good air quality. Typically, offices need between 6 to 10 air changes per hour, or ACH, to keep the indoor air fresh and healthy. For example, if you have a 3,000 cubic foot office space and you're aiming for 8 ACH, you would need about 400 cubic feet per minute of supply airflow. This helps to effectively ventilate the space and maintain good air quality. Moving on to ceiling diffusers, the typical throw distance, meaning how far the air can travel before it disperses, is usually between 4 to 6 meters. This range is important because it ensures the air is spread evenly across the occupied area. For instance, a diffuser supplying around 400 CFM can cover roughly 20 square meters, allowing for uniform air distribution. Finally, it's essential to consider air distribution and filter standards. Proper standards help us maintain not just comfort, but also health, especially in shared office environments. When we design or evaluate these systems, keeping these key points in mind ensures we create a safe, comfortable, and healthy indoor environment for everyone. Let's talk about air filters and their efficiencies. Pre-filters typically achieve around 80 to 90% efficiency for capturing particles that are between 5 and 10 micrometers in size. These are larger particles, like dust or pollen, and pre-filters help remove most of these before the air reaches more advanced filters. Speaking of advanced filters, HEPA filters are designed to be incredibly effective. They provide between 95 and 99.97% efficiency for particles as small as 0.3 micrometers. These tiny particles include fine contaminants, such as bacteria or some viruses, making HEPA filters critical for maintaining cleaner and healthier indoor environments. Now, moving on to air efficiency standards, the ASHRAE 62.1 standard specifies that each person should receive about 15 to 20 cubic feet per minute of fresh air. To put that into perspective, in a space with 20 people, you'd need around 400 CFM, cubic feet per minute, of fresh air supply to keep the environment comfortable and healthy. All of this ties back to our overall goal, ensuring good indoor air quality through proper filtration and ventilation standards. By understanding these efficiencies and requirements, we can better design systems that keep occupants safe and comfortable. Let's talk about the cooling tower and ventilation systems. These are crucial components in maintaining the efficiency and safety of our facility. The cooling tower helps dissipate heat from the process, ensuring that equipment runs within safe temperature ranges. Proper ventilation, on the other hand, is vital for controlling indoor air quality, removing excess heat, and preventing the buildup of harmful gases. When designed and maintained correctly, these systems not only improve operational performance, but also contribute to energy efficiency. As we've seen throughout this presentation, integrating effective cooling and ventilation solutions is essential for sustainable and safe plant operation. Now, let's talk about the difference between outlet water temperature and ambient wet bulb temperature, which is usually around 2 to 3 degrees Celsius. For example, if the wet bulb temperature is 29 degrees Celsius, then the outlet water temperature should be about 32 degrees Celsius, giving us what we call a 3-degree approach. This approach essentially shows how close the cooling tower gets to the ambient wet bulb temperature, and it's a key indicator of how efficiently the tower is operating. Next, we have the cooling tower approach, which is defined as the temperature difference between the inlet water and the outlet water. Typically, this difference ranges from 4 to 6 degrees Celsius. For instance, if the inlet water is at 37 degrees Celsius and the outlet water is at 32 degrees Celsius, that gives us a 5-degree range. This range is quite common in design and reflects how well the cooling tower is transferring heat from the water to the air. Finally, the cooling tower range is essentially the difference between the inlet and outlet water temperatures. It's a critical performance metric because it indicates the cooling capacity of the tower. A larger range generally means the tower is providing more cooling, but it also depends on the specific system requirements. Overall, these metrics, approach, range, and temperature differences, are vital for assessing cooling tower performance and ensuring efficient operation within the overall system. Let's talk about how we calculate efficiency in cooling towers. The formula is quite straightforward. Efficiency equals the range divided by the sum of range and approach, all multiplied by 100 to get a percentage. For example, if the range is 5 degrees C and the approach is 3 degrees C, then the efficiency would be 5 divided by 8 times 100, which gives us 62.5%. This helps us understand how effectively the cooling tower is performing. Now, moving on to evaporation loss. This is important because it directly impacts water consumption. Evaporation loss is estimated at about 1% of the circulation rate for every 5 degrees C of range. So, if you're circulating 1,000 liters per minute and your range is 5 degrees C, your evaporation loss would be around 10 liters per minute, just 1% of the total circulation. Understanding these performance metrics is crucial for assessing and optimizing the cooling tower's operation. These calculations help us identify efficiency gaps and water losses, guiding us towards better management and maintenance practices. Let's talk about ventilation and pressurization guidelines, starting with commercial kitchen hoods. They typically need about 75 to 100 CFM per square foot of hood area. For example, if you have a 2 by 2 foot hood, which is 4 square feet, it would require roughly 400 to 500 CFM of exhaust. This helps ensure proper removal of cooking fumes and heat, maintaining a safe and comfortable environment. Next, let's look at toilet areas. They generally require about 10 to 15 air changes per hour, or ACH. To put that into perspective, imagine a toilet space of 3,000 cubic feet. If we aim for 12 ACH, we need to exhaust about 600 CFM of air. This is crucial for controlling odors and maintaining good air quality. Overall, these guidelines help us design effective ventilation systems that keep indoor environments healthy and comfortable. Proper exhaust rates ensure contaminants are removed efficiently and that spaces are properly pressurized or exhausted as needed. Now, let's discuss lift lobbies and stairwells in terms of pressurization. Lift lobbies typically require a pressure of about 5 to 8 pascals to ensure both comfort and safety for occupants. A common value you'll often see is around 6 Pa, which helps maintain air freshness and, importantly, prevents smoke from entering the lobby during a fire or other emergency. Moving on to stairwells, these need to be maintained at a higher pressure, generally around 12 to 15 pascals. For example, 14 Pa is a typical figure used to ensure that smoke doesn't seep into the staircases, thereby keeping evacuation routes clear and safe during a fire. Overall, proper ventilation and pressurization are crucial for safety in these areas. They help protect occupants by controlling the movement of smoke and ensuring that escape routes remain accessible. These guidelines are a vital part of the overall fire safety strategy in any building. During fire emergencies, smoke exhaust systems typically operate at about 10 to 15 air changes per hour, or ACH. This rate helps to effectively clear smoke from the space and improve safety. For example, if we have a space that's 50,000 cubic feet, we need roughly 10,000 cubic feet per minute, or CFM, of airflow to clear the smoke quickly. You get this number by multiplying the volume by 12 and then dividing by 60, which converts it into CFM. Ensuring proper smoke exhaust during fires is crucial for protecting occupants and allowing safe evacuation. It's important to remember that these ventilation rates are designed to respond rapidly in emergencies, helping to maintain a safer environment until the situation is under control. HVAC thumb rules are actually derived from well-known organizations like ASHRAE, ISHRAE, and SMACNA, as well as from general industry practice. These rules are really meant for educational purposes and initial design ideas. They serve as a quick reference to get a sense of what's needed before diving into more precise calculations, whether that's with software or manual methods. So, while they're not exact, they're incredibly useful for guiding the early stages of HVAC planning and ensuring we stay on the right track. It's all about balancing efficiency and practicality before committing to detailed analysis. Thank you so much for being here today. I really appreciate your time and attention throughout this presentation. If you found this information valuable, I encourage you to subscribe for future updates and insights. Staying connected helps us continue sharing knowledge and resources that can make a real difference. Once again, thank you for your interest and engagement. I look forward to connecting with you again soon.